হ্যাঁ স্যার করে দিয়েছি স্যার I have started the recording.
হ্যাঁ স্টার্ট করবো তাই তো
হ্যাঁ স্যার
ওকে so good morning today we'll cover the last part of this stability and performance analysis of linear systems. As a quick recap, in the last class we have started with the feed forward PID control of nonlinear dynamic system for an example problem. There we have shown that if we consider the total excitation voltage to possess two components, one feed forward and one feedback, where the feed forward is the dominant part, modeled in terms of PID in this form, and also the response contains the demand part along with a small error, and the control objective would be to reduce this error to zero or near zero as quickly as possible. In this nonlinear problem, we made the substitutions of this voltage and this error to have a nonlinear to generate a nonlinear algebraic part in terms of a known demand profile, and that nonlinear algebraic part gave an estimate to for the feed forward voltage, and because of the approximations, when we give this voltage, exactly the demand won't be produced. There will be some error, and in order to kill that error, we have used a small feedback part, and the overall substitution of this R as D minus E and V as Vf plus Vb, along with the algebraic equation that we referred to for the demand, if we make use of both the equations, then one linearized error dynamic equation we obtained, and that from that linearized error dynamic equation, we tried to assess the roles for these different P, I, and D gains. Roughly speaking, in order to have a stable situation, the linearized dynamic equation should have all the coefficients as positive, and in order to make these coefficients positive, the gains could be manipulated appropriately. And as a way of obtaining the solution, we know for the response we substitute this kind of form to generate an algebraic equation for S, and by splitting that polynomial equation in S in this form, where these z's could be real or these z's could be complex, we obtain an algebraic equation, the root of which should be substituted for S in this response, and for each z there will be a leading constant term, and since this is a linear equation, all the individual solutions we can add together to obtain the full solution. And possibly one example we have given how to solve that equation. And here what we are trying to show is that a similar equation could be generated if we substitute this plant onto the Laplacian domain by making use of this substitution. Then this plant gets transformed to another Laplacian form where this GS is nothing but output by input, and by and this GS we call the transfer function if all the initial conditions are put to 0. In that way, we would be obtaining that transfer function in this form where the denominator polynomial is identical to what we have here. And this denominator polynomial, we call it the characteristic polynomial since its root decide the solution the way it will behave. Clearly, for stable solution, all the real parts of this S should be negative so that the error would decay with time. And when we equate this function to 0, we call that to be the characteristic equation, and the roots of the characteristic equations are called the poles. Here on a complex plane, we tried to show the poles for different kinds of systems. For a first order system of this kind, its root is minus sigma 1, so it will fall somewhere here. And as we have already discussed, that if the poles fall on this part of the complex plane, including the imaginary axis, then we can infer the system to be stable. But if it falls on the other side, the system would be unstable. So, if the first order equation, if its characteristic equation is like this, then for positive sigma, we will infer the system to be stable. If the system is of this nature, that is second order, then we have two possibilities. One, both the roots could be real, or both the roots could be a complex conjugate. One such form has been shown here. The root could be, if one root is sigma 2 W2, the other root will be sigma 2 minus W2. And we also, if we go here, higher the value of minus sigma, the decay of the response would be faster. So, if we compare between this first order system and this second order system, by virtue of the poles having further from the imaginary axis towards the left side, this second order system will be much faster because of having large value of sigma 2. If the system is of higher order, no matter what is its form, it could be split into possible first order and second order together. If it is a third order, 3 roots could be real, or 1 root could be real and 2 roots could be complex conjugate. So in that way, irrespective of the order of the system, these first order and second order systems are fundamentally important for analyzing the characteristic of the system. So this first nature, as a demonstration of that, we have given two kinds of variation. If this sigma 1 2 is less than sigma 1 1, here we see the error decays in a relatively slower manner in comparison to the other case. Here, a similar situation has been demonstrated for the second order characteristics. Here we also note that if we increase this sigma value, the response would decay faster, but the response may involve overshoot. So, if the overshoot is not acceptable for some system, then Uh, to what extent we can increase this sigma, it needs to be a part of the design of the controller. Uh, and as we have as for the stability, all the roots should be real. Then, I mean, if we write this equation in this form, then for all z to be negative, all this coefficient has to be positive. And if the coefficients are positive, already we have seen for first order and second order systems that that is sufficient for guaranteeing stability. Now here we have dealt with two examples of third order system. In one case, this is a characteristic function, and just by factorization, if we group this s cube plus 1 in one part and this s square plus s in another part, this s cube plus 1 is this, and this s square plus s is this. So if we take the common factor s plus 1, then the remaining part would be this, and its root will be minus 1 and plus minus j. So this minus 1 and plus minus j. So here positiveness of the coefficient is showing to be sufficient for guaranteeing stability. But next we have given another example of this type. Only the coefficients of s and the constant term, those have been changed, and if we group the equation in the same manner, then after factorization the roots appear to be in this form. So here we see these two roots corresponding to this fraction emerges on the right side of the complex plane, and as we know, if it falls on this side, it implies an unstable system. So clearly it shows that for a system whose order is more than 2, just positivity of the coefficient, it is not sufficient to guarantee stability. So we need to do something, and that something we discussed as applying Routh principle or Routh-Hurwitz principle, in which an array is formed from the characteristic equation in the shown manner. The first line we write by starting from the leftmost part of the characteristic function, and we pick the alternative coefficient 1, then a n minus 2, then a n minus 4. In this way we keep on proceeding, and the next line is generated by collecting the alternate coefficient starting from the second position. So this is how these first two lines are formed, and clearly if n is odd, that is, say it is, if it is s cube, then it will be s square, next will be s, next will be a constant term. So it will involve the constant term if n is odd, and here will, so I mean, depending on how many terms we have here, if we have say 8 terms, 4 will go to this group and 4 will go to this group. But if it has 7 terms, 4 will go to the top line and 3 will go to the next line, and the last entry of the second line will be a 0. So in this way, after we complete construction of the first 2 lines, then the third line is obtained in this way. I mean, we multiply this into this minus this into this and make a division by this. For the second coefficient, we multiply this with this and negative of this and divide by the same coefficient this. So in this way, the third line is formed, and if we name the coefficients of third line in this manner, the fourth line coefficient is obtained very much the same way. Here instead of we have the third line has been constructed on the basis of the first two lines. The fourth line will be constructed on the basis of second and third line. Fifth line will be constructed on the basis of third and fourth line, and in this way we proceed till end. I mean, if we consider the largest polynomial of the first line, that is s to the power of n. So in the second line, the largest polynomial will correspond to this Sn minus 1. So if we go by reducing the order of polynomial by 1, the last entry will be a constant, and in this way we will keep on generating the coefficient till the last one. As an example, we have considered the polynomial here. So here the first line coefficients will be this 1 and this 2, and the second line coefficient will be this 1, either this 8, and the second coefficient will be either this 8 or 2. So when we have 1, 2 and 1, 8, then this coefficient of S1 will be 1 into 2 minus 1 into 8, that is minus 6, divided by 1 that is minus 6. When we have 1, 2 and 1, 2, then 1 into 2 minus 1 into 2, that will lead to a 0. And we have also noted that if a 0 comes, then we replace that 0 by a small positive number epsilon, and we proceed for constructing the remaining coefficients. And this 0 has come out because 1 into 0 minus 1 into 0 would result into a 0 in the numerator. And for here, by considering this 1, 8 minus 6, 0, the coefficients will be minus 6 into 8, that is minus 48, minus 1 into 0. So again I am wrong here. It should be minus 6 into 8 divided by minus 6, so it will return 1, 8. And when it is epsilon, it will be epsilon into 8 divided by epsilon. Again, we will get back the same 8. So here we see in both the cases we obtain a stable system. And if we consider this s cube plus s square plus 2s plus 8 system, the example of which we have discussed here by factorization, we have clearly found that we have two roots that fall on the right side of the complex plane, and hence that results into an unstable system. Now here, after compiling the coefficients of the first column, the Routh-Hurwitz criteria, it says if all the coefficients are positive, then it would lead to a stable system. But if there is reversal of sign in the first column, then the system would be unstable, and the number of unstable poles would be equal to number of reversal of signs. So if we consider the first problem, here this is positive, this is negative. So one reversal of sign, and from negative to positive again second reversal. So we see there are two sign reversal in the first column. So there will be two unstable poles, and by the factorization we reach to the same conclusion. Here we have introduced this array without proof, but since we have introduced without proof, we are discussing one problem that shows that this observation, rather the statement that we have corresponding to the router array, is obeyed by what we see from direct factorization. And in the other case, when instead of 8 we have 2, we see 1, 1, epsilon and 8. So in this case, there is no sign reversal. So the system would be stable. And if we consider this equation SQ plus S square plus 2S plus 2, and if we group this first two term, if we take S square common, we get a factor S plus 1, and from these two, if I take a factor 2 common, then again we get S plus 1. So its factorization is simply S plus 1 into S square plus 2. So its root are minus 1 and plus minus j root 2. So two roots on the imaginary axis and one root on the left side. So really the system would become a stable one. So that is what we have discussed in the last class, and also in the last class the block diagram form of feedback feed forward control for a nonlinear system we have shown, and if the system is purely linear one, only the lower part of it would remain, and that kind of system was composed. And here a loop reduction algebra that was shown here. So if we have this kind of system, and then this RS by DS loop reduction, that is RS by DS as we have called, is the this complete transfer function. It is obtained in this form, and if in the limit where the constant term in the product of GS, CS and SS is much greater than 1, then basically the response would depend only on the sensor accuracy, and any uncertainties in the expression of the dynamics, system dynamics, would be absorbed. So that is a critical observation we could make through this loop reduction. And also the other effect of the loop reduction would be okay. If we consider just the characteristic, it is a whole rational polynomial. Normally, if we just look at this form, the resultant characteristic equation does not get any polynomial in the numerator, but as it is a straightforward plant like this. If we have a feedback loop between this, then if we have unity in the feedback loop, then the loop reduction would result in GS by 1 plus GS, and because of that kind of GS plus 1 by GS, the instead of a one here, what we'll be having is another polynomial in the numerator. So, and of course, the numerator polynomial would be of at least one order less than the denominator polynomial, and in fact, that would be the rational form for this kind of most general transfer function. And the way we are factorizing the denominator polynomial, in the similar way we could factorize the numerator polynomial, and the factors of the numerator polynomial are called zeros, whereas the factors of the denominator polynomial, as we have already told, we call those to be poles. Here we have considered the way of obtaining the solution for this kind of rational function, where we split the denominator in this form, and by again we multiply this together and we compare the coefficients of the denominator as well as the numerator to generate different equations for obtaining this P1 and P2 etc. And after obtaining the P1, P2, as we have told in the last class and also today, I mean, the solution would have two parts, one corresponding to this part, the other corresponding to this part, and by obtaining the coefficients by simple algebra, we would obtain the final solution, though this P1, P2, etc. could be complex, but if we process the whole equation, since it is a real system, ultimately the response would contain only real coefficients and real polynomials. And as we have seen, if that is what we are trying to say, this exponential term has a very crucial role in all this solution. If this exponential term, its argument is negative, then it implies decay. If it is positive, then it implies growth. So if it is the equation for error dynamics, we really require this to decay and go finally to zero or close to zero. So if we do not have this exponential term, if we have only cos and sine terms, then it implies that such situation will arise only in case we have poles on a complex conjugate pole on the imaginary axis, and in that case still the solution will remain bounded by the amplitude of this cosine and sine terms. So the presence of exponential would mean asymptotic decay to zero, and absence of this exponential term but presence of only these periodic terms would imply bounded stability by the amplitude of the periodic function. So these are two important observations that we require to continue further. So the next topic that we are going to discuss is this steady state error. So what that means, suppose we have this kind of system and we give a sinusoidal excitation to it. This is the plant including the controller part, and we know it's for it to be stable, its pole should lie on the negative side of the imaginary axis. And if we excite this plant with a sinusoidal function, then this sinusoidal function, it will have, I mean, sinusoidal functions are either s by s square plus omega square or omega by s square by omega square. So two poles on the real axis. So that part of the solution will stand even after the subsidence of the dynamics corresponding to this GS part. So if we excite a system with a sinusoidal input and if the system is stable, what we'll observe is after certain time transients will decay off and we'll be having a repetitive sinusoidal oscillation of same kind. And when we have that same kind of sinusoidal of oscillation, though it is not steady in real terms, in the control parlance, we call that to be the steady solution. Okay, so that steady solution is basically error dynamics in the limit t acquiring a large value. And the good part of the Laplace transformation is that we can infer the steady state error by this equation. How we obtain this equation? We have shown it in 2 lines next. For that, we consider this form of the function df/dt, and the first line we solve by the regular process of considering it to be the e to the power of minus st to be the first function and df/dt to be the second function. So, and by integrating the by parts, we go through this first line and obtain this final step. So here e to the power of minus st in the limit infinity, it will produce a 0, but in the limit 0, it will produce 1. And this df/dt integration will produce 0. So as a result of that, we get only this f0, and for the second part of the integration by parts, we obtain this particular form. So this is the first line we obtain, and in the second case, we just push this limit inside the integral, and if we put s is equal to 0, then it becomes 1. So it simply becomes df/dt into dt, and in the limit we obtain this form. So this and this are basically the product of the same initial state. So if we equate these two, we obtain the equation that you have given here. Limit this is equal to, in this form. So basically, limit et is equal to es, and for es we have written ds minus rs because of this unity feedback. So next, for this loop, what we do, we pull out this ds from here and we write 1 minus rs by ds, and this rs by ds we apply this form, and if we complete the algebra, then we obtain this form. Here next we are considering one unit step input demand, then dt is 1, its Laplacian transformation is 1 by s, and we are considering gs of this form, where this kp is basically, here we can conceive we have a proportional controller from which that kp has come, and this a square plus as plus b square is a property of this plant. If we assume that way, then the steady state error, this s into 1 by s, this 1 by s from this, and in the denominator this 1 plus is this, and then for GS we write here like this, and if we keep on continuing with the algebra in the numerator, this will result into a 1, and after that if we solve this, this will also come to the numerator, and in the denominator this will go here and 1 kp will come here, and if we put s is equal to 0, then the steady state error would become like this, and it clearly shows with increase in the proportional gain the steady state error will keep on decreasing. Now instead of a proportional gain, if we have an integral gain, then instead of kp here we will be having ki by s. So that is what we have done here. Instead of everything is same, instead of kp we have put ki by s, and the resulting equation has become like this, and we clearly see that the steady state error is going to 0. So in fact this part also we have discussed earlier, I believe. Here the role of the integral gain was to ensure a 0 steady error, but with only proportional gain. This because of this uncertainty, a steady state error would remain that you have discussed earlier. So in this approach we have verified that to evolve once more. So the inferences are, the proportional, the P gain, increase of P gain would give rise to decrease of steady error, but it won't result into a 0 steady state error. If we want a 0 steady state error, we have to involve one integral gain, and after that we are coming to the system response to sinusoidal input that we are talking about. So here the Laplace, in the Laplacian domain, the input is omega by omega square plus s square, and as we have told, if I consider this, then Rs is ds into gs, and for ds we put this, and gs remains as it is, and then we factorize this part corresponding to this. We have s plus j omega and s minus j omega, with the numerator written as q1 plus k2, and corresponding to the poles of gs, many other factors would emerge here, but as we have told, these poles lie on the imaginary axis, whereas each pole, for the stability, to fulfill the stability requirement, those will be on the left side of the imaginary axis. So their poles will, the effect of their poles will give a faster decay, I mean, just not faster decay, those will decay, whereas for this complex conjugate pole, a sinusoidal oscillation will persist. শুভম আমি ক্লাসে আছি গো, পরে কথা বলবো। So from the next part of the processing, the effect of these poles we are omitting, and just by the procedure described here, we obtain the coefficients K1 and K2, and by substituting those K1 and K2, we obtain the steady state solution. Why steady state solution? Because the effect of other poles we have not considered in this solution. And the notable part is that here this GS, corresponding to this GS, we have either G minus J omega or G plus J omega that has come out as a way of obtaining these constants K1 and K2. So this G J omega will basically have one real part and one imaginary part, and this together could be written in this form, where this M omega we call it either a gain or amplitude, and this phi we call it to be the phase difference. Again, I mean, if we have a solution of this nature, this solution, it could be written as a pure sinusoidal function plus some phase difference. Okay, because sin A cos B plus cos A sin B is equal to sin A plus B, and just, adding 1 by root 2 and 1 by root 2 here and multiplying with a root 2 here, that root 2 will remain as the amplitude, and this would be written as sine root 3 2 by 2 plus pi by 4 or minus pi by 4, whatever that will result. So basically this cos plus sine could be written as a pure sine function into a phase difference. So that is the form we are talking about. So corresponding to here, we'll be having cos and sine together, and those cos and sine together would be converted into just a pure sine function here, as we have written. So these are basically pure straightforward use of this algebra. In this algebra, M omega is, again we are calling it to be the magnitude of this Gj omega. So it will be real square this plus imaginary square this under root. And if we see the magnification of this J omega and G minus J omega remains the same thing, but when we go for the phase difference, here for G J omega it is imaginary part divided by the real part, and when we have minus G J omega, because of this negative t here, we'll be having a negative part coming out. So that is the result of the magnification part, and that is the result of the phase part corresponding to J omega and minus J omega. So if we make note of all these, then finally we obtain the steady solution in this form, and here this again I tell it is the magnification or gain part, and this is the phase part. And normally for the gain part we represent the gain in this form, and we call it to be the decibel, its unit. Why we do it, it will become clear as we give certain examples. I mean, do I need to elaborate on this algebraic part, or you just, I think it would be better if I just take, you will carry out the algebra by yourself, and if you find some problem, then you report to me and I will do the needful. The algebra is pretty straightforward, there is not much to be explained either. Now we have just considered a simple system like this. I mean, if we see this S will have an unit of 1 by second, so because of that we have just written a first order plant in non-dimensional form. This numerator, when the numerator is a constant, the denominator should also be a constant dimensionally. So here within the bracket we have 1 by second, and we have multiplied it by a second, so that the denominator also becomes a non-dimensional term, and that non-dimensional we do in terms of the time constant of the system. And then its phi will be simply minus omega tan inverse minus omega t1, and 20 log 10 m would be given by this term. I mean, this comes from by putting x is equal to j omega. So it is the imaginary part and it is the real part. And here we see the imaginary part divided by this 1 has resulted, and this negativity has come because this transfer function appears in the denominator. So when we raise it to the numerator, this j omega would become minus j omega, and in the numerator we will be getting a square plus b square like term. So that's why this negativity has come in the phase part, and in the gain it has come, and if we take this half in front we get 10, and because of this 1 by, for 1 we have a 0, and for the denominator we get the negative part. So that is how what we get for a pure first order system. So now for very low frequency excitation like this 20 log 10 m becomes like just 10 log 10 1, which is 0, and here also because of very low value of omega it is tan inverse a small value, that is phi is also near 0. But in the limit of much faster excitation, then we can neglect this 1 with respect to this omega t1 square, and this 20 log 10 becomes 10 log 10 omega t1 whole square, and this 2 comes out, that makes 20 log 10 omega t1, and the phi limit would go to minus pi by 2 because the denominator acquiring a very for very large omega, we are having tan inverse infinity kind of situation. That's why we are getting this minus pi by 2. And at 1 by t1, if we put it, this would give phi is equal to minus pi by 4. And from 10 log 10, we'll get this kind of value. So if we just consider this asymptote and this asymptote, these are the plots. This we call the corner plot, and the actual plot would follow closely this line, but in this region it will have some variation. Again, it will merge with this corner plot after some time. Similarly, for the phase plot, initially we have the similar term, similar variation, and finally also we have the variation close to the corner plot, and in between we have going from 0 through minus pi by 4 at 1, and then minus pi by 2 here. So these are the outcome of, these green lines we call the corner plots, which contain only the asymptotes, and by filling the by proper interpolation between these asymptotes, we generate the actual asymptotic plot. So this is the actual variation plot, and these are the corner plots. The corner plots are really helpful in other circumstances that we will read shortly. Now, for a second order system, similarly we write this GS and phi corresponding, we obtain this GS in this form. This is a pure second order term, and to have a constant, dimensionless denominator, we have pulled one by omega 2 square out, and then similarly by the division of by processing of the real and imaginary part, we obtain the equation for the phase and obtain the equation for the gain. And again, it is a pure, simple algebraic manipulation. This 1 minus omega by omega 2 square, it comes from the substitution of this j omega square here. So j square will give rise to 1, and this omega by omega 2 will lead to this form, and so that forms the real part. Its real part square is written here, and the imaginary part results from this. So that square you have written. So we get the form of 20 log 10 m in this form, and if we further process it, this log 10 one gives a 0, and the denominator gives a minus. This 20 into half gives us a 10, and this function we write here. And then again, in the similar manner, we construct the asymptote in the limit omega much less than omega 2 and omega much greater than omega 2, and the middle value we also process. So just to arrive at the inference that up to a certain level we have this kind of corner plot, and from 1 onward we obtain this kind of corner plot in the gain part, and for the phase part we have this kind of corner plot. Now here we can see that omega much greater than omega 2, what happens? It becomes if we consider here, it gives omega minus omega to the power of some problem, right? I mean, we'll see that this will, the argument will move through a positive value, then through negative value. And that kind of variation we can have only if the phi that is through third quadrant and then second quadrant. That's why here we infer for for the first part to be 0 and for the second part to be minus pi and the in between part to be minus pi by 2. I mean, what I mean to say here, tan inverse in both the cases, it is tan inverse 0, and for another 0, whether we assign minus pi or plus pi, that we decide based on the progression of this phi, that would be in the limit of, in this particular limit we'll see it will be through a positive coordinate, positive value, and tan remains positive only in the third quadrant. So that means the progression from 0 to that pi value, it goes through fourth quadrant first and then the third quadrant. So that's why we, from right after 0, we have progression up to minus pi by 2 and finally up to minus pi. So that is what we have plotted here. And here between these two denominator, we see here the decay is like 20 log 10, and whereas it is 40 log 10. So it is for by per decade means 1 to 10 or 10 to 100, etc. So for the first order term, we see a decay at the rate of 20 dB per decade, and for the second order, we see a decay at the rate of 40 dB per decade, and in the phase plot, we have a loss of phase of minus pi by 2 here for the first order, but for the second order, we have minus pi. Now we are considering a combination of first order numerator and the second order denominator. So then we will appreciate the importance of this log 10. So this log 10 will make it convenient that the numerator and the denominator part will get split out separately, and we can just join the corner plots for the numerator part and then denominator part one after another. So in the limit of small omega, we have this part, and then corresponding to this part, since it is not associated with any negative, we have an initial rise at the rate of 20 dB per decade, because the numerator is of the first order. Had it been in the denominator, we would have seen a 20 dB decay, but since it is in the numerator, we see a 20 dB per decade rise. And here we have considered this time constant T1 is smaller than the time constant T2. Sorry, time constant T1 is smaller and the time constant T2 is higher. So it is, the second order system is faster basically. And then corresponding to this second order term, we have this kind of corner plot with 40 dB per decade, but this starts after 10, because up to 10 we can consider the effect of the first order term remains dominant and the second order term starts taking its role only after we cross this T2 time. So it is basically T1 time, it is basically T2 time as we are plotting against omega T1. So that is how we construct the corner plot, and within the corner plot we fill it by the noted asymptotic variation to complete the actual plot. And this is the phase plot. The first we obtain the corner diagram. For the first order term we have this rise, first order numerator term, that is a zero term, and second order denominator term we have this fall, and next we complete this just by the other observations. So near 1 we'll be having pi by 4, and here to here we'll be having a loss of pi by 2, and then further pi by 2. And because of the pull of the second order interaction of the first order and second order, this won't remain a horizontal nature. This would be slightly falling shape, etc., etc. And if we make suitable note of that, we can interpolate the asymptotic plot by making good use of the corner plot. So that is what I have tried to say. The corner plot, those are having a very strong role, and all the time we have kept on repeating all the systems could be considered decomposed in terms of first order and second order. So if we know their property clearly, then once we know the corner plot, and then we can combine the corner plot in any manner and finally construct the phase gain plot of the system of any complicated nature. If this GS is a pure constant, what would have got? If this constant is greater than 1, there will be a constant here 20 log 10k. If k is a fraction, then it will be on this side. So by suitable addition of a constant term, that is like a proportional constant in the controller, we could shift the corner plot by the superposition of another constant, so everything will get shifted upward. If the constant line is upward, if the constant line is downward, everything will have a downward pull, and the phase plane won't get affected by the addition of any constant in the numerator. So those notes are given here, and with these notes we go to the final phase of the presentation, that is gain margin and phase margin. I mean, if the phase lag is 180 degree, it implies when we ask for growth, we get a decay, and when we ask for a decay, we get a growth. So the output is completely corrupt. So because of that, the phase lag of 180 degree is considered totally unacceptable. Maybe in the same manner, if the gain part we see, the gain part 1 means what we require, what we demand, we achieve that much gain. This M part is the ratio, it emerges from the input output ratio part. Okay, so M is equal to 1 means if the demanded amplitude is 1, the response amplitude will also be 1. That is very much desired. But if this gain term falls below 1, what it means, the amplitude of the response is lower than the amplitude in the demand. So there is an attenuation. If the M part is greater than 1, it would imply we are having a magnified presence of the amplitude in comparison to the denominator. Neither is good. Basically, M close to 1 is the requirement. So basically, that is what we need to ensure by the proper design of the system. Here we have considered a system where we have a numerator, first order term, and in the denominator a first order as well as a second order, and their time constants are separated in this manner. So for the numerator we get a growth at 20 dB per decade because it is first order. Then for the first part of the denominator we get a 40 dB per decade decay, and for the third part we get a 20 dB per decade decay. And similarly in the gain part for the numerator we get a phase lead by pi by 2, and then a phase lag by pi, and finally for the first order denominator term we get another lag by pi by 2. So that is how we first plot the corner plot, then we complete it by filling this part I have failed to fill. There should be a curvature like thing here as well, but that is of not much consequence in the discussion that we are going to make here. So as we are telling, up to unity gain, if that is acceptable, so this is the point where after which the gain will undergo an attenuation, and because of this attenuation, an attenuation beyond a point won't be acceptable. So this particular point we call it the gain crossover frequency, and the phase at this particular point we call it to be the phase margin. And as we have told, minus pi is a very bad thing. So for phase margin, this gap we consider to be the phase margin, and this phase margin, it is better if it is well within 90 degrees, because 180 degree is real bad. 90 degree is at least some kind of compromise. So normally the acceptable gain margin, phase margin of pi by 2 up to pi by 2 is acceptable. Even if it is pi by 4 or so, it is even better. And in case of gain margin, where we have the phase crossing or reaching this minus pi level, corresponding to that we have a phase crossover frequency, and at the phase crossover frequency point, the margin of gain, we describe that to be the gain margin. And here in this particular system, the gain margin is between this minus 20 and minus 40, close to this minus 40. So roughly speaking, I have written it to be about 38 dB or so. But so much attenuation is also not good. About 6 dB normally we consider to be acceptable. So if this is the situation, what is the way out? Here we see the gain margin, I mean it is about 38 dB, but we cannot allow it to be more than 6 dB. So what we need to do, we need to introduce a proportionality constant that will jack it upward, and the gain margin will simply it don't make change to this plot. So this upward shift should be such that here instead of 38 dB, this line would cross at around 5 dB or 6 dB. So if we jack it up by say another 34 or 5 degrees, we resolve the problem. The other situation could be we just, if this time constant is in our hand, we will just make this T3, we just interchange this T2 and T3. That will also, you'll see, it will resolve the problem of the gain crossover frequency. So in this manner, this Bode plot exercise helps us in reaching us to a conclusion regarding the design of the overall control system. So with this note, today I stop, unless and until you have, if you have any question. Any question? So should I stop today?